Can you see the screen? Okay. So do you remember where we stopped last class? Hello, we were discussing about how to choose an RTOS. Okay, yes. When you choose an RTOS, what are the points that we should consider while choosing an RTOS? And we have to consider two things, that is the functional requirements as well as the non-functional requirements. So both the functional as well as the non-functional requirements must be analyzed when we are choosing an RTOS. And when we choose an RTOS, that RTOS should suit the particular application for which we are developing, the application that we are going to develop. So, and without proper support from the RTOS, we cannot develop the application properly. So we have to ensure that both the functional as well as non-functional requirements are met by the RTOS. So what are the functional requirements? Yesterday, I think we had discussed the functional requirements to be met. And the functional requirements, it includes processor support, that is the RTOS that we choose should be supported by the processor on the machine. Then the memory requirements, that is there should be the minimal RAM and ROM requirements for the OS. Then the real-time capabilities of the RTOS, that is it should consider the whether the standards are met by the OS, the real-time capabilities are met by the OS. Then kernel and interrupt latency, that is there can be certain in RTOS, most of the functions in the system, they happen with the help of interrupts. And whenever an interrupt occurs, the time taken to service those interrupts should be reduced. And if the time taken to service the interrupt is called interrupt latency, and that should be minimal. Then inter-process communication and task synchronization, since there are several processes running on the system, it should be able to perform, the RTOS should be able to properly synchronize these tasks together. And there is task synchronization and task scheduling models by RTOS, which we will discuss in the next section. Then the modularization support. So here as I said earlier, in microkernel architecture, several only the essential features are incorporated in the OS, others are implemented as the services, and these services, they can be separately modified and recompiled, and this constitutes support for modularity. And if there is modularity support, we can choose the RTOS for those applications that needs modular programming support. An example of an RTOS that supports modularity is WinCE. Then next is support for networking and communication. That is, if our product needs needs to communicate with other devices, or if it is using network protocols, then you should ensure that it is supported by the RTOS. Then development languages, and those there are certain languages like Java. We have runtime libraries built into the system, and so if we have such support, then choosing that particular language, we should ensure that the OS also supports that language. So these are the functional requirements that we considered in RTOS. Then what are the non-functional requirements? Now, non-functional requirements, it is not directly related to the functions that the system perform, but some additional things that may affect our system. And that is called non-functional requirements. It doesn't have direct influence on the functionality of the system. That is, if the product is functioning properly, or the language used, nor the hardware support. We have no such issues related to that in non-functional requirements. In this section, in non-functional requirements, we address those factors that affect our system from the outside. That is not from within the system, but some factors influencing the system from outside. And this includes to check if it is custom developed or off the shelf. And custom developed or off the shelf means they're ready-made softwares which are available, or ready-made hardware components available. And if it is available, if we have products easily available, then you can buy the product and assemble the system. So depending on the OS requirement, it is possible to go for the complete development of OS suited for the embedded application, or we must check whether the things or components are readily available. So and if the readily available components matches with the system requirements, we can easily purchase it from the market. Otherwise, we will have to go for developing the components. So this choice depends on the choice of whether to buy or to develop. It depends on the development cost, then the licensing fee, development time, and availability of skilled resource personnel. So depending on all these factors, whether the development cost is high or low, whether licensing fee is available and the cost of the licensing fee, then development time and availability of the skilled resource person, we decide whether we have to develop the product or develop the complete environment, or to buy off-the-shelf components. Off-the-shelf components are ready-made components available in the market. So this is one factor. Depending on the cost and time, we have to decide how the system, whether the OS provides all these supports for those components that we buy from the market. The next is cost. So the total cost of developing or debugging the operating system, it needs to be evaluated before selecting the OS. So whether you have to take a ready-made OS or if you have to assemble the programs, it depends on the cost. Then developing and debugging tools availability. For some OS, there may be superior in performance, but the availability of tools may not be there. So for the development purpose will not be there. So it will be limited. So it may take a lot of time to develop using those operating systems. So development and debugging tools availability should be checked while choosing an OS. Then ease of use. That is, it is an important feature that needs to be considered while selecting RTOS that is commercially available. There are, as I said, there are certain RTOS that are commercially available, and we can assemble components into that. And when we assemble components into the RTOS, the RTOS should properly support these off-the-shelf components, and also it should be easy to use. Then after sales is for commercial embedded RTOS. Then after sales in the form of email, on-call service. That is, if any problem arises, we have to contact the concerned third party, and in the form of email, or on call, you can call them for service, etc., for fixing the bugs and for supporting the production issues, etc. And all these only with proper support, we need to choose an RTOS. If an RTOS doesn't provide a proper support for development purpose, then we cannot choose that particular RTOS. Only if proper support is available for developing a product, then we can choose that particular RTOS. So these are the different non-functional requirements. So this is not related to the functioning of the embedded product, but it indirectly affects the development process. So the non-functional requirements to be considered include whether the OS needs to be custom developed. Custom developed means whether we should develop that or we should buy it from outside. Off the shelf is ready-made components or ready-made software that we purchase from outside. So this includes custom developed or off the shelf. The next issue is non-functional requirement is cost. Then the third one is development and debugging tools availability. Then the fourth is ease of use. And fifth one is after sales. So these are the 5 different non-functional requirements to be satisfied while choosing an RTOS. So we had discussed the functional and non-functional requirements while choosing an RTOS. So this is a 4-mark question. Just remember that it's a 4-mark question and it's an important question in this module. How to choose an RTOS. And it is mentioned in the syllabus also, like the same heading, how to choose an RTOS. Okay. So can you say what are the non-functional requirements while choosing an RTOS? Anyone? What are the non-functional requirements while choosing an RTOS? Okay, cost, Then ease of use, cost, ease of use, cost, after sales service. Uh, the RTOS that we are using should the third party should support us in the development process. And ease of use, okay, development and debugging tools availability. If there are no debugging tools available, then it will be difficult for testing the system. Then cost, and first one is custom developed. Custom developed means, well, we should develop our own OS, or we should go for an OS that is already developed by somebody else, and that is off the shelf. That is what we call it as off the shelf software. Okay. Is it clear? And in short, this custom build or off the shelf, it is shortened as COTS, COTS, COTS. In most of the software engineering books, it is shortened as COTS, COTS, custom build or off the shelf software, COTS software. Custom built or off the shelf. It is shortened as COTS, COTS. Okay. Is it clear? So now we are going to the next section. So we have covered the introductory section, the introduction of RTOS and how to choose an RTOS and all. Now we are going to the next section, that is interrupt handling in RTOS. Can you see the screen? Hello? Okay. So let us go on to the section, interrupt routines in RTOS environment and handling of interrupt service calls. We have, you might have studied what are interrupts, what are interrupt service routines, ISRs, and handling of interrupt service calls. Now, normally, how is an interrupt handled by the system? What is an interrupt? Can anyone say what is an interrupt? What are interrupts? Anyone, you might have studied in microcontrollers and all. Can you name one interrupt routine, name of an interrupt? Okay, some request or some request to the processor to stop its current execution and execute some other routine. It is a request to the processor, and processor might be executing a task or a process at a particular moment in time. So but in certain cases, during some emergency and all, the normal execution of the processor must be stopped, and it should perform or it should execute some other routine. So in that case, to interrupt the processor or send a request to the processor, we have certain mechanisms called interrupts, and these interrupts, it will request the processor to stop its execution and to continue with or execute some other important task. So the tasks that are to be executed when an interrupt arrives is called the interrupt service routines. Interrupt service routines. So you might have studied INT 5.5, 6.5, 7.5, trap, etc. in 8085. There are several interrupts arising in microprocessors. So these interrupts have their own priorities also. The highest priority interrupt must be executed as soon as it arrives. So whenever a high priority interrupt arrives, the processor will stop its current execution and it will start executing the highest priority interrupt. And that executing the highest priority interrupt means the processor will jump to another routine, and there is the program counter will be set to the starting address of another routine, and it will start executing. And that routine to which the processor jumps is called the interrupt service routine. And on completion of that interrupt service routine, it will return back to its normal execution. Is it clear? So now how in that is in normal RTOS, and this happens in real-time RTOS also. So how are these interrupts handled in RTOS? So let us see what is the difference in RTOS, the based for the interrupt service calls in RTOS. Okay, how can these interrupt service calls handled in RTOS, handling of interrupt service calls? So in RTOS, the ISR functions as follows, or ISR means the interrupt service routines. In RTOS, it functions as follows. So these are the three main points that we should consider when we speak of interrupt service routines in RTOS. That is, the first point is it has higher priority over OS functions and all application tasks. Whenever an interrupt arrives in an RTOS, it has higher priority than other OS functions and application tasks. So interrupts in RTOS has higher priority than the application tasks as well as other OS functions. Then there is first point. So that which means that whenever an interrupt arrives, it must be serviced. Then second point is that it does not wait for any semaphore, mailbox message or queue messages. So if something is going on, if the processor is currently waiting for a semaphore or a mailbox, etc., this interrupt doesn't wait for any of these because they are of the highest priority, and so it will not wait for any semaphore, mailbox message or queue messages. Then third is it does not wait for mutex. You know, these are all mutual exclusion. We have studied in mutual exclusion. It does not wait for mutex. Else it has to wait for other critical section code to finish. So it cannot wait for any critical section code to finish because it has higher priority, and this ISR should run first if it arrives. So these are the 3 points that should be considered in RTOS while servicing interrupt service routines in RTOS. That is, it has higher priority over OS functions and other application tasks. It does not wait for semaphore or any mailbox messages or queue messages, and it does not wait for mutex. So since it should run first before any other code executes. Is it clear? Is it clear? The 3 points? Okay. What are the 3 points? What was the first point? What was the first point regarding interrupts in RTOS, interrupt service routines in RTOS? It has higher priority than any other functions, operating system functions, then as well as user application tasks. Then second point, does not wait for semaphore, and also it does not wait for mutex or any critical section to complete. Okay. So these are the 3 main features of ISRs in RTOS. Then, how does an RTOS respond to interrupts? And that is what we are going to study next. Response to hardware source calls on interrupts by OSs, by RTOSs. That is here in embedded systems, we said that it is a combination of both hardware and firmware. So mostly the devices detect certain events and pass those events to the RTOS. So mostly the interrupts will be hardware interrupts, and how the system responds to these hardware source calls on interrupts. So what are the 3 methods? Here there are 3 ways in which the RTOS responds to a hardware source call or an interrupt call. There are 3 alternative systems that that needs to be considered when processing requests, hardware interrupt service requests. So what are the 3 alternatives for handling interrupt calls? The first one is direct call to an ISR by an interrupting source and interrupt service routine sending an interrupt service request. So I'm sure you didn't understand anything here because the first mechanism, direct call to ISR, you can break this sentence and study what it is, okay? Because it is a confusing sentence. This is the textbook sentence, because most of the evaluators, they look at textbook sentences. So I didn't alter the sentence. If you are changing the sentence, then they might think that you're not writing the correct answer. So I just didn't modify the sentence. I'm giving you the sentence as it is, because the evaluators also, they study the same sentence, and when they value the paper, they will be looking for the same sentences. So first is direct call to an ISR. Direct call to an ISR means whenever an interrupt arrives, instead of calling the operating system to service the routine, the system will directly call the interrupt service routine. The system is not calling the operating system to service the ISR, but the system is directly calling the interrupt service routine. Usually, we send a request to the operating system, and this operating system will stop the execution of the currently running process which the processor is running, and then it will switch on to the interrupt service routine. But in this first mechanism, the operating system is not involved. Instead, the system directly services the interrupt service routine, and from the interrupting source. The direct call to ISR by an interrupting source. So if there is an interrupt occurring in the system, and that source is called the interrupt source. Once a request arrives on any of the pins of the ICs that we are using for embedded product development, if an interrupt request arrives, then instead of going to the operating system, it will go directly to the ISR routine. And the ISR, before starting its execution, it will send an enter message to the operating system to inform the operating system that it has started operating, so that the operating system will stop the current execution. So that message that is sent to the operating system is called interrupt service message. So the first point, I'll repeat it once again. Direct call to ISR by the interrupting source. The interrupting source, instead of calling giving a request to the operating system, it will call the interrupt service routine directly. It will jump to the interrupt service routine directly, and the interrupt service routine, before starting its execution, it will send an interrupt service request, ISR enter message. ISR enter message is interrupt service request enter message, and that is called ISM, interrupt service message, to the operating system. And when the operating system receives this interrupt service message, it will stop its execution, and then the interrupt service routine will run. And on completion, it will return a message back to the operating system that it has completed its execution. Okay, is it clear, the first point? Is it clear to you? Okay, Ashwati, can you just summarize what I said in that first point? It is a complicated sentence. What is the meaning of that sentence? Okay, the source that gives the request is called the interrupt source. The source from where the interrupt arrives is called the interrupting source. And this interrupting source, it will give a request, and that's called the interrupt service request. And this request, it doesn't go directly to the operating system. Yes, the ISR doesn't go directly to the operating system. Instead, it will go directly to the interrupt service routine. And once the interrupt service routine gets this request, it will send an ISR enter message. That is, the ISR is going to be executed. So that message is called ISR enter message, ISM, and shortened as ISM. It is sent to the RTOS, and RTOS will stop its execution. RTOS, the processor has been executing some process currently. It will stop its execution, and the interrupt service routine will run. After completion of the interrupt service routine, it will again send a message back to the RTOS, so that the processor can continue its execution. Is it clear? Hello, is it clear? Okay, Fabina. Now, this is one mechanism. Instead of directly going to the RTOS and requesting to service the interrupt service routine, the interrupting source is directly calling the interrupt service routine. And once the interrupt service routine is called, the interrupt service routine itself will send an enter message to the RTOS so that the RTOS will stop executing the currently running process by the processor. And then once it receives the ISR message, it will stop, and then the ISR will start execution. And on completion of the ISR, again a message is sent to the RTOS to resume its execution. That is the first method, direct call to ISR by the interrupting source. The interrupting source is directly calling the interrupt service routine. Then second method is RTOS first getting interrupted on an interrupt. That is, instead of going to the ISR directly, the RTOS is getting interrupted. That is, the request is going to the RTOS. And so the RTOS now gets interrupted once an interrupt arrives. And then the OS, that is the RTOS, calls the ISR as what we see in normal cases. That is, the RTOS is getting interrupted when an interrupt arrives, which means the interrupting source is directly sending request to the RTOS first, and then the RTOS calls the ISR. This is easy to understand, isn't it? I think that sentence is easy, isn't it? Did you understand that? Okay, instead of directly calling the ISR as in the first method, the second method, the interrupting source will directly send a request to the RTOS, and the RTOS will call the ISR. Okay, now after only when the RTOS calls the ISR will start its execution and return back to RTOS. This is what is done in normal cases. And then the third one is RTOS first interrupting on an interrupt. And that is the RTOS. The request is again sent to the RTOS, and then the RTOS will initiate an ISR. It will initiate one ISR, that is an interrupt service routine. This interrupt service routine is not directly related to the request that has arrived, but it is another interrupt service routine. This routine will check the priority of the interrupt that has arrived, and then it will call the ISR. So there is an intermediate ISR running. This intermediate ISR will call the ISR if it has higher priority. So RTOS, again, the request is sent to the RTOS. RTOS will not service the ISR directly, but instead it will initiate another ISR, and this ISR, it will check the priority of the currently arrived interrupt, and then if the priority is high, then it will call the ISR. Is it clear? So it's a two-step process. Here we said RTOS interrupt is directly going to RTOS. RTOS will invoke the ISR. But here, again, the request is going directly to the RTOS, but RTOS will call another ISR, which checks for the priority of the interrupt that has arrived. And if the priority is high, then it will call the corresponding interrupt. Is it clear? Did you understand the third one? Hello? Ashwati, if you can't understand, I will repeat it. Hello? Ashwati, can you hear? Amrita, anyone please respond? Hello? Okay. I'll repeat the third one once more. Here, in this second method, I said the interrupt service routine is directly giving a request to the RTOS, that is our operating system, and the operating system will jump to the ISR as the request comes, and it will process. But in this case, again, the first step is the same. The interrupt service request is going to the RTOS. The RTOS is getting interrupted on an interrupt. That means the interrupting source is interrupting the RTOS first. The sending request to the RTOS. Interrupting the RTOS means it is the interrupt source is sending a request to the RTOS. But RTOS is not directly going to service the interrupt now, but instead it will call another ISR. the RTOS will initiate the ISR, which calls the ISR that has arrived. So RTOS will initiate an ISR, and this ISR checks the priority of the currently arrived interrupt, and then if the priority is high, then it will call the interrupt that has arrived. So instead of directly servicing the interrupt by the instead of directly servicing the ISR, the RTOS will call an intermediate ISR, and this ISR will check the priority and then call the ISR that has arrived if it has higher priority than the currently running task. Okay. So RTOS getting interrupted on an interrupt. The RTOS is getting interrupted means the interrupt source is sending a request to the RTOS. So it is getting interrupted. And then it will initiate first, instead of jumping directly to the ISR, it will initiate another ISR. And this ISR will check the priority of the interrupt service routine that has interrupt request that has arrived. And then if it has high priority, then it will call the ISR. So the sentence is grammatically, it is difficult to understand. That's why I'm explaining it. That is RTOS first getting interrupted on an interrupt. Then RTOS initiates the ISR, which calls an ISR, means another ISR which has higher priority. So it's a three-step process. So the first method is direct call to ISR. The interrupt service interrupting source is directly sending a request to the interrupt service routine, and it will start execution. No priority is checked. It will start execution, and it will send a message to the OS to stop its execution. Second is RTOS is the interrupt service routine is sending request to the RTOS, and then the RTOS is calling the ISR. Third is, again, the interrupt service request is sent to the RTOS, but the RTOS initiates another ISR, which checks for the priority of the currently arrived interrupt, and then it calls the interrupt service routine that has corresponding to the interrupt that has arrived. Okay. Is it clear? Hello, is it clear? Okay, now we have to discuss the three mechanisms, the diagrammatic representation of the three mechanisms in detail. So before that, if I start it now, it's a big process. So we'll start in the next class, the three mechanisms. So now you may take your attendance, please. Number one. Okay, number two. Okay, number three. Answer. Number 6. Number 7. Number 8. Number 9. Number 11. Number 12. Number 13. Number 14. Number 16. Number 17. 18. 20. 22. 23. 24. 26. 27. 28. 29. 30. 30, Amrita. Okay. 31, 32, Didna. 33. Number 33, Harita. Number 3, Amal. Okay, Harita, I think she's here in the meet. Okay. So all are present. Okay. Thank you.